Hello friends, welcome to lecture 2 from Digital Logic Design on number systems. Now we should discuss about number system conversions. Basically there are four types of number systems. The first one binary, second one decimal, third one octal, fourth one hexadecimal. We can convert one kind of number system into another type of number system. We can convert the binary numbers into decimal, octal and hexadecimal. So totally three conversions we can do. Similarly for decimal number system, binary, octal and hexadecimal. Again 3. The same way octal to binary, decimal and hexadecimal 3. Next with hexadecimal also we can convert into binary, decimal and octal. Again 3. Totally we can do full conversions with these four number systems. So let us discuss in this video regarding binary number system into decimal, octal and hexadecimal. In the next videos, we should discuss about the remaining conversion methods. Okay. Here the first one is binary to decimal conversion. To do this binary to decimal conversion, let us consider the binary weights for integer part starting from 2 power 0, 2 power 1, 2 power 2 and 2 power 3. For fractional part 2 power minus 1, 2 power minus 2, 2 power minus 3. To do the conversion from binary to decimal, we should multiply each bit in the given number with the corresponding binary weight on both sides and then add. So let us see one example. Here the given question is 1011.101 with base 2. We have to convert into decimal number system. To solve this problem, first let us rewrite the given binary values 1011.101. In this, the left side part is integer part, the right side part is fractional part. The whole number itself is a floating number. First, we should assign binary weights for each bit. Whenever we are going to assign the binary weights for integer part, always the process starts from LSB. For integer part, this is LSB, least significant bit. This leftmost one is MSB, most significant bit. So always we should assign the binary weight starting from LSB towards MSB only. Similarly for fractional part, we should assign the binary weights from MSB to LSB. Now we should assign the binary weights. This is 2 power 0, this is 2 power 1, this is 2 power 2, this is 2 power 3. For fractional part, the binary weight should be 2 power minus 1, 2 power minus 2, 2 power minus 3. Now we should multiply each bit with the corresponding binary weight and then add. So for integer part, the leftmost MSB bit is 1 into 2 power 3 plus 0 into 2 power 2 plus 1 into 2 power 1 plus 1 into 2 power 0 plus fractional part also we should add 1 into 2 power minus 1 plus 0 into 2 power minus 2 plus 1 into 2 power minus 3. Now we should calculate the value. This is 8 plus 0 plus 2 plus 1 plus 1 by 2 plus 1 by 4 plus 1 by 8. 11.875 with the base 10. This is a decimal number. Therefore, the answer is 1011.101 with the base 2, which is equal to 11.875 with the base 10. This is the solution for this given problem. Next one, binary to octal conversion. To convert binary number into octal conversion, first, what is meant by octal? Octal means 8. 8 we should write in terms of power of 2. So, it is equal to 2 power 3. That means it requires totally 3 bits to represent one octal digit. In the same way, to get the equivalent octal digit for the given binary values, we need to make 3 bits into a group from LSB towards MSB for integer part and make 3 bits into a group from MSB towards LSB for fractional part. Let us solve this problem. 1011.101. This is our given binary number. Now we should make 3 bits as one group starting from LSB for integer part. This is one group. Similarly, from the next bit, we should make another group with the leftmost 3 bits. But here only one bit is there. To fill this group with the 3 bits, we should keep leftmost 2 bits as zeros. In the same way, for fractional part, starting from MSB, this is MSB, this is MSB. From this, we should move towards right side, else LSB. This is another group. Now we should write the equivalent octal digit for each group. Octal means 3 bits only we should use, so that to write the equivalent octal digit, we should apply 3 binary weights only, 2 power 0, 2 power 1, 2 power 2. So with the help of these binary weights, we should prepare the truth table to write the equivalent octal digit. So first combination is 0, 0, 0. The equivalent octal digit is 0. If it is 0, 0, 1, 1 means the equivalent binary weight is 1 only, so that the equivalent octal digit is 1. Similarly, 0, 1, 0 means in the place of 2, we have 1, so that the equivalent value is 2 because its equivalent binary weight is 2. Similarly, 0, 1, 1 means 1 plus 0, 1, 1 means the equivalent value is 2 binary weight. The equivalent value for this 1 is 1 binary weight, so 2 plus 1 equal to 3. Similarly, in the place of 4, we have 1, 1, 0, 0. Its value is 4. Similarly, 4 plus 1 is 5. 1, 1, 0 means 6. 1, 1, 1 is 7. With the help of this truth table, we can write equivalent octal digit. 0, 0, 1 means its equivalent octal digit is 1. This is 0, 1, 1. This is 3. 1, 0, 1 is 5. 13.5 with base 8. This is our octal number. Another method also you can follow to write the equivalent octal digit. So for each group, just you should apply binary weights 2 power 0, 2 power 1, 2 power 2. This is 2 power 0, 2 power 1, 2 power 2. Similarly, this is 2 power 0, this is 2 power 1, 2 power 2. Now we should multiply each bit with the corresponding binary weights and then add. So here these two bits are zeros, so that no need to multiply. So 1 into 2 power 0 is 1. Therefore, its value is 1. Similarly, here 0. Therefore, we should add only the remaining 2 bits. 2 power 1 into 1, 2 plus 2 power 0 is 1. 1 into 1 is 1. 2 plus 1 is 3. Okay. In the same way, 2 power 2 is 4 plus 2 power 0 is 1. 1 into 1 is 1. Okay. Here 0. So its equivalent is 4 plus 1 is 5. In this way also we can find the octal value. Clear? Next one. Binary to hexadecimal conversion. Same process you should follow. Just like binary to octal. Hexadecimal means 16. 16 equal to 2 power 4. So that 4 bits are required to make a group. And also with the help of truth table also we can write the equivalent hexadecimal number. Okay. 2 power 0, 2 power 1, 2 power 2, 2 power 3. Because 4 bits are required, so that 4 binary weights we have to take to write the equivalent hexadecimal number. Clear? This is our given number. Now we should split into groups. This is integer part starting from LSP, these 4 first group and these 4 second group. Similarly, with the help of these 2 bits, by inserting another 2 zeros, we can make third group. Okay. Similarly, for fractional part also, this is MSP, this is LSP. From MSP to LSP, we should move to make the groups. This is first group, left to right. Next, here 101, only 3 bits we have, so that we should keep one more 0 towards right side only. Next, this is the second group. Okay. Whenever we keep 2 zeros left side, there is no change in the value of the given binary. So in the same way, when we put zeros towards right side in the fractional part after decimal point, also it doesn't change the value of the given binary. Now we should write the equivalent hexadecimal digit. There are 2 methods with the help of this table or the help of just simply apply the binary weights for each group and then calculate the equivalent hexadecimal value. 2 power 0, 2 power 1, 2 power 2, 2 power 3. Similarly, 2 power 0, 2 power 1, 2 power 2, 2 power 3. In this way, we should write for each group. Okay. Now we should write the equivalent hexadecimal value. So 1 only here. So 1 equivalent binary weight is 2 power 1 is 2. Therefore, its equivalent hexadecimal digit is 2. For the second group, 1, 1, 1, 2 power 2 is 4 plus 2 power 1 is 2, 6 plus 2 power 0 is 1. Therefore, its equivalent hexadecimal digit is 7. Next, 1, 0, 1, 1. The same way, 1 means 2 power 3, 8 plus 2 power 1 is 2, 10 plus 2 power 0 is 1. Therefore, its equivalent value is 11. But in hexadecimal, we never use 11 directly. In hexadecimal number system, we have 0 to 9 decimal digits and then A, B, C, D, E and F. Okay, A means 10, B is 11, C 12, D 13, E 14, F 15. Now we should replace 11 with the equivalent alphabetic letter only. So we should write B instead of this 11. Okay. Next, for fractional part 1101, again 1101 means 2 power 3, 8 plus 2 power 2 4 12 plus 2 power 0 is 1, so that its equivalent value is 13. 13th equivalent alphabetic letter is D. Therefore, we should write D as a hexadecimal digit. Similarly, 1010 means 1 means 2 power 3, 8 plus 2 power 1 is 2, 10. 10 means its equivalent alphabetic letter is A only. Therefore, we should write A. Okay. This is our hexadecimal value. Therefore, the answer is 27B.DA with base 16. Clear? With this, the total 3 conversions from binary to decimal, octal and hexadecimal number are completed. I hope you understand this concept. In the next video, I will provide you the remaining conversions. If you like my video, please like, share and subscribe to my channel. Thank you.